Okay, let's look at how we analyse data after a practical result has been done. So before we start that though, there's a key difference here between precision and accuracy. So precision here refers to how repeatable the results are, how close together the results are as a group. So imagine this target here, we've got high precision here because of the fact they're grouped together really closely, and so one after the other, each trial has been very consistent. So they're very precise in terms of the data there. Whereas here we've got fairly low precision because they're quite spread out. So from one result to the next there was no consistency, so the precision there is low. Okay? Now in terms of accuracy though, accuracy is how close to the correct value or the true value were the results. So here, even though the precision was high, the accuracy was low. It wasn't very accurate, okay? Because it's a fair way off what the true value should have been where the centre target there is representing it. All right? Here we've got poor precision because of the spread, but the accuracy when you average these out would have been quite close to the middle there. So in terms of a total result here, you got an accurate result at the end there, but your results were quite inconsistent in achieving that. So low precision, but accurate. Over here, if you look at this one, this actually has got poor precision because there's big scatter going on, and also if you look at the accuracy, if you average those values, you're going to be somewhere out here, and therefore it's not accurate either. Whereas this last one, the precision is very high because repeatedly they're close together, there's a very small scatter in the results, and it's very accurate because it's on the value of what you should be getting. Okay, so bear those things in mind. Okay, the best way of looking at this analysis then, the effects of errors on the data or the results, is to look at some examples. So what we've got here is a power pack, which could be set at 2 to 12 volts, and we're going to measure the voltage going in there more accurately with using a voltmeter, and we're going to use an ammeter there to measure the current. So something like this device here. So if your results are similar to this here, we've got some data points there, and we've got a line of best fit drawn in with a needed amount of scatter with those data points above and below the line. You should get an idea that there's some random errors here that's going on, because they should all sit on the line pretty much if there was very little random errors. So that means the precision there, or how precise the results are, isn't terribly good. It's not horrible, but it's not great either. So obviously the further away they are, that's a bigger indication of larger random errors and less precise results. Okay, so that's one thing you talk about. So when we're doing this and we're talking about the fact that there's some scatter here, it means that you've got some random errors, and you should try and identify which of those could have caused that effect. So looking at this here, the only two measurements we're making is current and voltage there. So why would the current and voltage have some random errors? So in the first place, if you look at the sort of dials, if you're using an analog meter here, you'll find there's dashes there going around that meter. And sometimes you'll find that the arrow is in between there and you have to round up or round down when you've done your results. So that could be a small random error there if you've decided to do that. Or it might just miss the dash there, or the smallest increment that you can measure to. All right. Apart from that, you can get a parallax error, because if you read the needle from different angles here, you'll find that the current reads a bit bigger than you're supposed to get, or a bit smaller. So it's really important you try and actually read this from dead on in front of the meter with the background straight behind it. So that's another reason you can get random error. But the effect on the data from those random errors is to cause this sort of scatter around the line of best fit, okay, and cause it to be less precise in your readings. It wouldn't be very repeatable then. Okay. One of the ways to improve it then would be to actually repeat and average your readings for your current and also your voltmeter. And if you do that, you'll find your precision improves, and you'll end up with the crosses going closer to that line of best fit, hopefully, by doing the averaging processes. So if I saw something like that, you'd say the precision was a lot better because it's getting that trend line and it's actually sitting on it like it's supposed to then. Okay. You haven't got as much spread of results. Now let's look at the effect of systematic errors instead. So systematic errors are when the data is consistently higher than it should have been, or consistently lower than it should have been. So for example here, it's possible that ammeter started above the origin here, or above zero rather. So you had a non-zero ammeter there, or non-zero instrument. And if that was the case here, let's say it was a half amp it started off on instead of zero, every one of your values were actually a half an amp bigger than they should have been. All of your data points would have been pushed up like that by half an amp. And so that would move your intercept for your y-intercept, and obviously that would affect the accuracy of your experiment here, because you should have got that going through zero, because current and voltage should be proportional. So it affects your accuracy. So just bear in mind that systematic errors affect accuracy. And you can see that if your trend line has missed the zero when it shouldn't have. Okay, so there could be other reasons for this. It's possible that these ammeters had a blown resistor in there, and the lab assistants actually replaced that with another resistor of a slightly different size, and so 5 amps actually turns out to be 4.2 amps, so it's not calibrated correctly then. So one of the ways of overcoming these systematic errors would be to replace the equipment and try it again. Okay, so that's a common way of doing it. You can improve your systematic errors and your accuracy by replacing the equipment and repeating it with that equipment. Now, on top of that, I guess there's another experiment we could look at. Here we've got a pendulum, and we're trying to measure the period, the time it takes to go backwards and forwards once. So we could actually measure the length of the pendulum here and have that fixed on a point, let the actual ball go and have it backwards and forwards, and we'll measure the period of that pendulum with that ball at the end or that bob at the end. All right, so just one recording backwards and forwards with a stopwatch, and you'll get some stuff there. Now, that will have some random errors, which will be shown by the scatter on the graph, you know, the scatter of the data points, because of the fact you might suddenly start the stopwatch too soon, or start it too late, or stop it too late, or stop it too soon. So sometimes your time will be bigger than it's supposed to be, and sometimes smaller. So that's a random one. So repeating and averaging will reduce that random error and improve your precision. Okay. The other way of doing it is to do 10 of these, have it go backwards and forwards 10 times, and divide by 10, and that'll give you an average, and that should move your data points closer to your line and improve precision. This student's got a different problem. They've got a problem with systematic error here because they should have measured to the centre of the pendulum bob here at that point, and they haven't. They've stopped at the start of where that ball starts. So they're actually this far too short with their length on every single reading. So every one of their lengths is shorter, so that would move your graph, your line of best fit, above or below that origin. In this case, I think it's below because the length is actually shorter. So in this case, to improve the systematic error, you don't need to replace the rule that you're using to actually do your measurements. You need to actually change your procedure so that you actually include that extra bit of length there. Okay, so that's a bit unusual for a systematic error. Most people just say replace the equipment. But here it's an issue with your procedure, not realising you need to go to the centre of that bob. Okay. Obviously the random errors are going to occur here still by the way as well, because it's very hard to put your rule on the start of there for a 0 and at the end of there when you do this each time. It's going to be a couple of millimetres out in each trial, sometimes bigger, sometimes smaller, so that's going to be your precision affected. This is sort of an example of a bit of random error going on there, a bit of scatter, so therefore it's probably due to that something in your measuring of the equipment. So your precision here, not perfect, but you could find out your accuracy to be pretty good. It just might turn out that you've got no systematic errors. The other one you could do is you might end up, this one here is an example of one where the random errors are still present there, there's still some scatter there, but your accuracy's out. Something's caused a systematic error there. Okay, so they're the ways you should be doing it. We're focusing now on what are the effects of errors on our data and results. So you need to look at it from those 2 points of view. Random and precision sort of go together, and the systematic ones affect the accuracy. Okay, thank you.